that we can ask about this matrix, first thing we want to ask is, for what values of b is the equation ax equals b consistent? In other words, when am I going to have a solution to this matrix vector equation? And if you remember, what set of vectors answers this question? Or what did we call this set of such vectors? Well, remember that if ax is equal to b, in other words, if this equation over here has a solution, what does that mean? Well, when I multiply the matrix A by the vector x, what I'm really getting is some linear combination, however many columns my matrix happens to have. In our case, our matrix only has 2 columns, so let me just write it like that. When I multiply a matrix by a vector, I'm getting a linear combination of its columns. So in this example, x1 times the column vector 1, negative 1, plus x2 times the column vector 2, negative 2, is then equal to b. And so we can say that b is a linear combination, LC, of the columns of A, 1, negative 1, and 2, negative 2. And because these are the columns of A, the set of such vectors, B, the set of linear combinations of the columns of the matrix, is called the column space of A. And just to bring our earlier vocabulary back into it, if B is a linear combination of the columns of this matrix, how can I rephrase this statement using the word span?
B is within the span of 1, negative 1, and 2, negative 2.
Exactly. B lives within the span of those 2 vectors, 1, negative 1, and 2, negative 2. B is an element of the span of those 2 vectors. So, that's actually our definition of what the column space of a matrix is. The column space of a matrix is exactly the span of its columns. Now, taking a look at our particular example, the columns of our matrix, 1, negative 1, and 2, negative 2, well, there's one of them. There's 1, negative 1. And the other one, 2, negative 2, what relationship do those 2 columns have to one another?
They share the same column.
They share, right, they're actually on the same line. In fact, to use a geometric word, they're parallel. And because they're parallel, what did we conclude, by the way, a couple days ago? If the columns of a matrix are parallel vectors, what's the determinant of that matrix? 0. Which is certainly the case for our matrix here. This determinant is negative 2 minus negative 2, 0. But now look on the right-hand side here, in our codomain, I have my 2 vectors. And the set of all their linear combinations makes up the column space. But because these vectors are parallel, the only places that we can get to by taking linear combinations of the columns of A are places that are along that line, shared by the 2 columns. So here, this is a graphical depiction of the column space of A. It's that line passing through the origin. And so for any B that lives within that line, AX equals B is going to have a solution. But it's also, this is a question that came up the other day. Okay, fine. The column space of a matrix is the span of its columns, but how do we write that answer? How can we communicate to someone else what the column space of a matrix is? How might we phrase our answer? Well, one of the ways of doing that is just to write it as the span of the columns. That's a completely valid way of describing a set. And it's actually going to be a way that we hang on to quite a bit. So the answer to this question is that those B that make this equation consistent is all B that live in the span of the vectors 1, -1 and 2, -2. So that's one way of writing the answer. It's just writing here's a span of two vectors that gives us the column space of A. But that almost seems too easy, because then we could just take any matrix, and if I want to know what the column space is, I can just write it's the span of, and then write the columns of the matrix. But where we want to push this today a little bit is to answer the following question: is it really necessary for us to include both of these columns in the span?
No,
Since they're parallel to one another, don't I get the same thing if I forget one of these vectors or the other? If I just were to write the span of, let's just say we cross out the second one, 1, -1, is the span of 1, -1 the same thing as the span of both 1, -1 and 2, -2? So let's see if we can answer that question. So if I'm trying to show that two sets are equal to one another, my first set being the span of 1, -1, let's call that set something. Let's call it, I don't know, U. And my second set is the span of both of those vectors. So let's call that set something else. Let's call it V, let's say. And I want to know whether these two sets are equal one to another. How do we have to prove that? Thinking back to your proofs and set theory, etc. course, if I'm trying to show that two sets are equal to one another, what's my burden of proof?
They have to have the same subsets.
They have to have the same subsets, and in particular, every element that belongs to one of these sets must also belong to the other. Right. So that's a two-part statement. I need to show that every element that belongs to U also belongs to V, and I have to show that every element that belongs to V also belongs to U. So let's see if we can do that. One of these directions is going to be simpler than the other. Let's take the first. I want to show that U is a subset of V. How do you show that one set is a subset of another set? What's their method of proof here?
They share the same elements.
Well, they don't have to have the same elements, but every element in U has to belong to V. So in other words, we're trying to show that for all vectors, and let's call them U, in U, we want to show that that vector U also must belong to V. So how do you begin a proof like this? If I want to begin the proof of this statement for all U, for all vectors U in the set capital U, we want to show that U belongs to V. So where does this proof begin? We're trying to prove the universal statement here for all vectors little u. So what should we do first? We should choose an arbitrary u. And I'm saying arbitrary here so that our conclusion will be true for all vectors u. So choose an arbitrary u in the set capital U. And then we ask ourselves, well, what do we know about U? And now that we know that it belongs to the set capital U, and capital U is the span of the vector 1, negative 1. So what does that mean that U looks like? What is it equal to if it's in the span of the vector 1, minus 1? What does U have to look like? What's the span mean again? It's the, well, it's not really, we've lost our matrix here. We're just looking at a couple of spans, okay, of a set of vectors. But what does span mean in the first place? It's the set of all linear combinations. It's a set of all linear combinations of, in this case, just the vector 1 minus 1. So in other words, U is going to be some constant times 1 minus 1 plus, but we don't have anything else. We don't have any other vectors in this set. So every U that belongs to the span of 1 minus 1 must be a multiple of the vector 1 minus 1. So it's got to look like C times 1 minus 1 for some C, for some constant C. So this is what our vector U looks like. But what are we trying to show? We're trying to show that U belongs to V. In other words, we're trying to show that it belongs to the span of the vectors 1 minus 1 and 2 minus 2. In other words, we need to show that U is a linear combination of both the vectors 1 minus 1 and 2 minus 2.
Could you just use couldn't you prove it just by using a number for C?
Well, not exactly, because again, we want this statement to be true for all U. But I'll agree with you about this, is that if what we're trying to do is to prove that U belongs to V, the span of both of these vectors, then it is sufficient to show that U is some linear combination, even if it's a particular linear combination, of the vectors 1 minus 1 and 2 minus 2. So here's what I mean by that. In order to prove the claim that U belongs to V, what I need to do is I need to show that there are coefficients I need to show that there are coefficients such that U is equal to some coefficient times 1 minus 1 plus some coefficient times 2 minus 2. So to diagram out what we have here, because U belongs to the set capital U, it's a multiple of the vector 1 minus 1, linear combination of the vector 1 minus 1. What we're trying to show is that it is also a linear combination of 1 minus 1 and 2 minus 2. So there's a question mark over this equal sign. If we can prove that this is true, then U must belong to V, which is what we're trying to prove if our contention is that capital U is a subset of capital V. So my question to you is, given that we know that we have assumed that U is C times 1 negative 1, explain to me why, so this is the part we're trying to prove, why is it equal to something times 1 minus 1 plus something times 2 minus 2? How can I fill in those two boxes to guarantee that this equal sign is true? What can I put in the first box? Well, that's not necessarily true, right? Because we don't necessarily know that that's going to match up with what I have on the left. Or at the very least, we need to do some more work to prove that.
Does it have to be the same number?
Yeah, the point is that we need this equality here to hold. So the vector we have here on the left-hand side has to equal the vector we have on the right-hand side. How do I fill in those two boxes to make that happen? Where should I put C?
In front of
If I put a C in front of 1 minus 1, then in order to guarantee the left and right-hand sides of this equation are equal, what should I put in front of 2 minus 2?
0.
And we've guaranteed now that the left-hand side and the right-hand side are equal to one another. And it looks silly, because, well, of course, if I put a 0 in front of the 2, negative 2, it's just going to make that vector drop away. But what's the difference in philosophy? On the left-hand side, we're looking at an element of the span of the vector 1 minus 1. So we're looking at an element of capital U. But on the right-hand side, we're looking at a linear combination of 1 minus 1 and 2 minus 2. So it's an element of V. But what we've just proven here is that, I'll write this in English here, every linear combination of 1 minus 1 is also a linear combination of both the vectors 1 minus 1 and 2 minus 2. And that guarantees that U is a subset of V. So that's the first step. So let's take a look at how to prove the backwards containment. Now that we've shown that U is a subset of V, we need to also show that V is a subset of U in order to establish the equality of both sets. To establish the second step, we just need to go backwards. To show that V is a subset of U, what we should do is show that for all vectors little v belonging to capital V, we want to show that V must also belong to U. And our tactic is the same, because we're trying to prove a statement which is based on a universal claim for all vectors V. So because this is a universal claim, we need to start our proof with, suppose V, or actually let me word it the same way I worded it before, choose an arbitrary. And when I say arbitrary here, that prevents us from choosing a single example, like 2 times the first vector plus 6 times the second vector. When I say arbitrary, that means that the particular linear combination that we're going to choose out of V has to have arbitrary coefficients. So because V belongs to capital V, by definition, V is a linear combination of those two columns, or those two vectors, right? Because we've lost our matrix here. But it's a linear combination of 1, negative 1, and 2, negative 2. And the coefficients of this linear combination are arbitrary. And what I mean by that is we're going to call them not by number, but by name. So let's say that this is C1 times the first vector plus C2 times the second vector. So this is how we have now come to meet our vector, little v, an arbitrary element of the set capital V, which is the span of these two vectors. And what we want to show is we want to show that V belongs to U. And to show that V belongs to U, we would have to establish that it is equal to some linear combination of just the vector 1 minus 1. So what we're trying to do here is show that this is equal to something times the vector 1 minus 1. If we can fill in that box with something, then we have proven this claim. So what multiple of 1, negative 1 is V equal to? Or how could I investigate that question?
C1 plus C2 of 2.
Yeah, let's take that left-hand side there. Let's multiply it out. Let's expand C1 times 1, negative 1 plus C2 times 2, negative 2. If I expand that out, I'm going to get 1 times C1 plus 2 times C2 in my first entry. And then in my second entry, I'm going to get negative 1 times C1 plus negative 2 times C2. And again, the question is this a multiple of the vector 1 minus 1? And if so, what multiple is it? Well, are we any closer to figuring out what multiple we're looking at? Kinda. Well, take a look at this vector on the left-hand side. What's the relationship between its first coordinate and its second coordinate? Well, second is the opposite of the first. So let's,
Cancel out.
well, kinda, right. Instead of cancel, though, I would say factor. Let's factor out C1 plus 2C2 out of this vector. C1 plus 2C2. If I factor that out of my first term, I just get 1. And if I factor C1 plus 2C2 out of my second term, what do I end up with? Negative 1. And miracle of miracles, we've now shown, so this same C1 plus 2C2 therefore proves our result, 2C2. So in other words, any linear combination of 1, negative 1 and 2, negative 2 can be written as a multiple of 1, negative 1. Namely, the multiple we need is C1 plus 2C2. And therefore, any vector which belongs to the span of the two vectors, 1, negative 1 and 2, negative 2, in other words, belongs to V, must therefore also belong to U, the span of just 1, negative 1. So we've established that U and V are equal as sets, and therefore, to get a little bit of space to write this conclusion, what we've really shown is that the span of just the vector 1 minus 1 is the same thing, is the same set as the span of both the vectors 1 minus 1 and 2 minus 2. So, in other words, if I'm going to describe the column space of the matrix 1, 2, negative 1, negative 2, if I'm going to describe the column space of this matrix, a priori, in the beginning, what we know is we know that that column space is the span of this column and that column. So in the beginning, we could just say, oh, of course, it's the span of those two columns. But it is much simpler. Because these are the same set, we might as well just get rid of that second column. We might just say that it's redundant. Because there's no place in the xy plane that both of these vectors can get to that one of them cannot get to by itself. That 2, negative 2 is redundant. We don't need it to describe our column space. All we need is the span of 1, negative 1. So what we would say in this example is that 1, negative 1 is, let's call it a minimal, because we've gotten rid of everything which was redundant, spanning set. It's the least number of vectors that it takes to describe the entirety of this column space we're trying to describe here. So it spans. Everything in the column space is a linear combination of 1, negative 1, but it's also minimal in the sense that we're explaining this with as few vectors as possible. And a minimal spanning set for a vector space or a vector subspace is called a basis. So the completely verbose way of answering this question, if the question is, what is the column space of this matrix? Usually, when we expect an answer that looks like this, we'll say it explicitly. What is a basis for the column space of A? And the answer is the vector 1, minus 1, the set consisting of the vector 1, minus 1.